Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today. I keep watching this game in the background, as it is every day here in my virtual classroom. If you step on inside, guys, we are going to learn a little bit more about polynomials. We've been doing a whole module or unit or whatever, if you will, on distributing polynomials, multiplying and foiling and kind of expanding them and going this way. We're going to work backwards now, and there is great benefit to working backwards when it comes to solving these things out, solving them, and we're going to get to solving some of them today as well, especially when they are in what's called quadratic form. So we are going to be working on greatest common factors in this video, and we're going to be working on something called the zero product property. Now, I do want to let you know that in this video here, I have a great set of problems, I think 26 or so, a great set of problems where eventually it becomes a little bit of drill and kill. I think I have something to introduce from one problem to another, but if you feel like I'm not introducing enough on the problem set, guys, check the description section, not just for this PDF, but also for some other YouTube videos that I have that are a little more lecture heavy with a little less examples on the actual nature of finding a greatest common factor and even zero product property if you need to do that. Okay, so anyway, I'm going to go ahead and jump into this though right now. We're going to start off with greatest common factor stuff right here, where we are going to factor the polynomial by finding the greatest common factor. Get it in standard form if it's not already. I want to start by getting in standard form before I factor, and factor out any negative leading coefficients. That should say negative, not negative. Negative leading coefficients there. All right, let's start with number one, 32b plus 8. Now, can I combine like terms? Can I simplify this any further? No, this is as fully simplified as can be. In fact, maybe it's too simplified. Maybe before this step that we see here, perhaps this was something else at one point. Let's discover its origins, shall we? Let's work backwards into maybe something distributed to make this. You know distributive property? You know, see, there's this word factor right here. Factor seems to be the opposite of what distributing is. If distributing means taking something and multiplying it into different terms to get the result as a product and adding them, kind of like this right here, that's what we're looking at right now. This 32b plus 8 is kind of like this. The question is kind of, what was it before? What was it before when something was multiplying to become these two values as they are? Now, there's more than one answer that you could have here. For example, I could have multiplied 2 with something to get 32 and 2 with something to get 8, and I would have had something there. But is 2 the largest number I could have multiplied in both these? No, there's a bigger number. 4? Maybe look a little bigger. Let's see how big we can get there, and that's the goal. We're going to find what's called the greatest common factor. Greatest meaning the largest number we can pull out, and common meaning something that we can pull out of both of them. Factor mean pulling them out as well. So greatest common factor asks us, what is the largest number that can divide out of 32 and 8? That's kind of the question. What's the largest number that can divide out of 32 and 8? And really, there are ways to do this, and I'm not going to get into the great breakdown. What I want you to do is I want you to know. I want you to test until you know. But the answer is 8. 8 can divide out of 32. 8 can divide out of 8. So, you know, what we're going to do here is we're going to write this in its factored form. We're going to take an 8 and divide it out of both of these numbers, but not like this. Right? I'm not going to make the numbers smaller, or I'm not going to make the expression smaller. I'm going to factor the 8 out through division, meaning 8 would multiply with the two numbers here that make 32b and that make 8. And really, factoring again, it's an anti-distribution. You're saying 8 times what gives us 32b. If it helps you, that's the way I like to say it. 8 times what gives us 32b? Well, 8 times 4 is 32, and that, you know, times b would give you the 32b right there, right? So just the b goes inside there, and 8 times 4b is 32b. And 8 times what gives us 8? Because remember, you factor that 8 out. You don't just, you know, cross it out and it's gone. That turns into 1, right? 8 times 1 is 8, and that's what we get there. It becomes 4b plus 1. And that's our goal. That's what we were trying to do. We were trying to factor something out. We did. This is an expression, which means this is equivalent to what this thing is right here, and that's your final answer. This is the factored form, the anti-distribution, if you will, what I would have to distribute to get into here. And remember, there's more than one thing that could have distributed. This could have been 2 times 16b plus 4. Imagine why I put that 16b, because 2 times 16b is 32b. 2 times 4 is 8. This could have been 4 times, let's see, 8b plus 2, because 4 times 8b is 32b, 4 times 2 is 8. All those are proper factors, but it's not the greatest common factor. It's not the largest number I could have pulled out of both those terms, and an 8 is exactly that. So the 8 was the largest one. That's what we go for there. All right, number 2, same exact kind of thing right here. Now we are in standard form, and that's a good first step here. So if you ask what I can divide 5 and 15 by at largest, you would say 5. Now I'm going to write this in red, not because it's wrong, but I'm just going to say it's not complete. If I divide a 5 or factor a 5 out of here, you might ask yourself what remains. 5 times what gives us negative 5n? Well, negative 1n would go there, and 5 times what is 15? Well, 3 is that. And this says factor. Don't get me wrong. I pulled out a 5 and this all works. But I did leave an instruction here that says factor out negative leading coefficients. That's one reason I'm asking you to put it in standard form, to say if your leading number is negative, you want to factor out the negative. Don't take my word for it, guys. Or take my word for it for now, but don't take my word for it later and try it for yourself and see where it's going to haunt you later to not factor out that negative. I promise you it's going to help you in the end, and it's something that's really expected of you to do. You don't want negative leading coefficients when you're factoring. So here's what I'm going to do. Instead of factoring out just a 5, guys, I'm going to factor out a negative 5. And when you factor a negative 5 out, you just have to be careful. Just ask yourself negative 5 times what gives us your numbers. So negative 5 times what gives us negative 5n? Well, negative 5 times n gives us negative 5n, right? So you're looking at what to distribute here. And negative 5 times what is positive 15. Well, negative times a negative will give us a positive, and remember that's a 3 that goes there. Negative 5 times negative 3 is positive 15, and that's factoring out that negative, and that's a better final result to put there. Factoring the negative out. And I'm going to do that anytime that we have something in standard form where the leading term is negative. You'll never see me not do that. All right, you'll never see me not do that. All right, number 3, here we go. 35a to the 4th plus 30a squared. Now, if we're going for what is the largest number that can divide out of 35 and 30, that value is 5. So what I'm going to write in red a little one more time. Again, this isn't wrong, but it's just incomplete. If I factor a 5 out, 5 times 7 is 35 and with an a to the 4th there, and 5 times 6 is 30 with an a squared there. And you say, hey, I'm good, I factored the 5 out. And you're not wrong. You factored out the largest number you could out of both of these. There's no issue with negatives. The 5, there's no problem with that 5 part. There's zero problem with it. It's not incorrect, it's incomplete. You have to factor out anything that multiplies, that multiplies into both of these things here. What's the largest things I can divide out of here? And it's not just the 5. You have to consider the fact that there are also these a's here, a to the 4th power. There are 4 powers of a right here, and there are 2 powers of a right here. You want to factor out all of the a's that you can. You want to factor out all of the a's that you can. So I still want to factor out that 5, y'all. That 5 can divide out of 35 and 30. But you know what? What's the most amount of a's that you can factor out of a to the 4th and a squared? The answer is 2. You can factor as many as 2 out of both of them, right? You could factor 4 out of this, but you can only factor 2 out of this one, so you got to take the lowest common denominator, if you will. So a squared can factor out of both of these, because you want to ask what still remains in these after you divide all that stuff out. And my better way to do it, instead of saying this divided by this, I like to say 5a squared times what gives us 35a to the 4th. So let's go with numbers first. Again, 5 times 7 is 35. And a squared times a squared is a to the 4th, because 2 plus 2 is 4. So that remains inside there. And then the next term, plus 5 times 6 is 30. And then a squared times, 1 is a squared, right? So you're just left with that 6 there. 5a squared times 6 is 30a squared, and that's that final result there. So once again, guys, this factoring business, it's kind of this whole idea of what numbers can factor out, what variables can factor out, and what remains. This, you can always double check it, but I am kind of double checking when I ask 5a squared times what is that. That's the number I'm writing to double check. you distribute, you would get that back out. So it is the opposite of what we're doing there with distribution. I am already at about the 10-minute mark and only 3 problems in, so you'll see where this will speed up as you kind of see more problems. So let's do this problem kind of faster now that we've recognized that one. We're trying to see what we can divide out of both the 6 and the 48, and what we can divide out of both the n cubed and the n squared. One thing at a time, we'll start with numbers. You can divide both 6 and 48 by 6. So I can take that 6 out, and n cubed and n squared, at most I can take out n squared, 2 powers of n. So 6n squared is factored out, and 6n squared times what is 6n cubed? Well, 6 times 1 is 6, and n squared times n is n cubed. So you get 6, so n, that's what remains in there, just a single n. 48n squared, 6 times 8 is 48. And then n squared, there's an n squared there. So you're done with that. That would be your final answer. And again, I'm just kind of whizzing through now. All right, now we have, still standard form. Now we have 2 variables here, x to the 4th y, and we have x squared without a y there in that one. Interesting. Okay, so 27 and 45. You know, you could divide a 3 out of both of them. A 9. I think 9 is going to be the largest thing we could divide out. So yeah, let's go ahead and factor a 9 out of the 27 and the 45. And x to the 4th y and x squared. Again, you're factoring out as much as you can, but it has to exist in all the variables you're factoring things out of. I don't have a y in this term right here. So I can't factor this y out of both terms because I don't have a y here. So I'm just going to leave that y inside the quantity when everything's factored out. I have 4 powers of x here and 2 powers of x here. I can factor out as much as an x squared. We've seen a lot of these so far. And that's all that I can factor out. So let's see what remains inside. 9 times 3 is 27. X squared times x squared is x to the 4th. And then no y could factor out here, so that y is still inside there. So 9x squared times 3x squared y is 27x to the 4th y. That's that first term. I know it's looking a little confusing here. We're going to get to some trinomials with single variables after this. And then the 45x squared here, we have 9x squared times what gives us 45x squared? Well, times 5. 9 times 5 is 45, and we got a greatest common factor of 9 pulled out with that x squared. You really got to ask yourself after you do this is not only just is it correct, but is it complete? And when you look back inside here, just ask yourself, is there anything else I can factor out of both of these terms? Clearly the answer is no. Nothing else you could factor. You've completely factored it. All right, number 6, 8ab to the 4th plus 32ab cubed. Looks like it's still in standard form because this is degree 5 and that's degree 4th. That's good. We haven't had to change anything yet. I forget if there are some. I think there will be some. All right, anyway, so right here, looks like an 8 can divide out of both. How about, let's see, there's an a here and an a here. So that a can factor out of both of them there, and a b to the 4th and a b cubed. So at most I can pull out 3 powers of b right there. And let's see what remains here, guys. 8 times 1 is 8. A times 1 is a, and b cubed times b gives us b to the 4th. So that's all that remains there, just a single b. When you multiply that with that, you get this. And then 8 times 4 is 32, and then the ab cubed all pulled out of there. So that's all that's left. It's just that b plus 4. That's not a 6, by the way. That's a b. So 8ab cubed times b plus 4 in that quantity. So the multiple variable things can get maybe a little confusing, but listen, as you can tell, guys, I'm just doing one thing at a time. I'm going number, and then the a's, and then the b's. So it can't get too confusing if you just know what remains. All right, now let's go to some trinomials with single variables. I think you'd probably much prefer this one. Now check this out. I have an x squared here, an x here, and no x's here. It's a standard quadratic trinomial. Without any x here, that means x is not a common factor among all 3 terms. You need to find something among all 3 terms. X's will not be able to pull out, so no x's. You'll still be left with an x squared and an x and a constant inside of there. But what's the largest number that can divide among these 3? And it has to divide among all 3. See, between 30 and 24, you could divide out a 6. But when 21 jumps into play, you can't divide it by 6. So there's got to be, another number, hopefully. And there is. You can divide these all by 3. So I'm going to factor a 3 out of there. And it looks like that's all I can factor out, guys. Nothing else can pull out of this thing. No x's because you got to do it for all 3 terms. So what remains inside? 3 times 10 is 30, and there's still the x squared. 3 times 8 is 24, and there's still the x. And 3 times 7 is 21. And that's it. And once again, you go and you ask yourself, look inside this quantity right here and say, is there any other common factor of the numbers I can pull out? No. Is there any other common factor of the variables I can pull out? No, I never was able to. So there's that. Number 8, on the other hand, if you look at these k's here, each term seems to have a k in it. So it looks like I am going to be able to have a common factor of at least 1 power of k. And it looks like at most I will only be able to factor out 1 power of k, while these ones will just have to have some things remaining. Now, number-wise, 21, 21, and negative 7, I just want to factor out, looks like a 7 from here. This is in standard form. This is a positive coefficient, so I'll factor out a 7 for sure, as they can divide by those. And then k to the 4th, k squared, and k. At most, I can just pull out a k from there. So 7k. So what remains? 7 times 3 is 21. K times k cubed is k to the 4th. Plus 7 times 3, once again, is 21. And then k times k is k squared. Okay? And then 7 times what is negative? 7k times what is negative 7k? Well, that'd be a negative 1 right there. That's what would have to go in there. Right? Always double check, guys. Try and distribute that stuff back in and see that it gets what you know how to do through distribution. There it is. Still got 4 more. No, wow. I still got 6 more greatest common factor problems. So again, I know I'm going slowly through this stuff, but these are the nitty-gritty bits. All right, got a cubic, quadratic, linear, and constant. Still standard form right here. Whew, these numbers are getting a little big, but it looks like these all divide by 8, if you know your multiples of 8 there. But a big quadrinomial. So here's a real big test for you on those things in greatest common factors. It escalated quickly. It sure did. So I can divide these all by 8, so factoring out the 8 there. I could have factored an n out of these, but this is a constant, so I'm not just going to choose a few to factor out if I got a factor of all 4 terms at the same time. And n appears to not have be a greatest common factor among all 4 terms. 8 is all I can pull out. I'm left with, looks like 9n cubed plus 8 times 1 is 8. So n squared, 1n squared. Plus looks like 5n. At this point, I'm going to go a little bit faster on these. 8 times 5n is 40n. And 8 times negative 7 is negative 56. There you go. And once again, look inside there. Ask yourself if there's anything else you can factor. To me, clearly not. I don't know about you. All right, here we go. Number 10. Okay, this one's not in standard form. So I'm going to go ahead and flip-flop these a little bit here. I'm going to put 12m to the 9th first. And then it looks like just reverse order. Plus 12m to the 5th. Minus 10m to the 4th plus 18m cubed. Okay, so the numbers, well, 12, 12, 18 would have been a 3, but there's a 10. I can divide these by 2. At most, I can factor a 2 out of here. So out comes a 2. They do all have m's. What's the lowest power of m's? M cubed. So I'm going to factor that m cubed out. All right, let's see. 2 times 6 is 12. M cubed times m to the 6th is m to the 9th. Once again, you got to remember you're adding the exponents there, right? You're adding them, so it's it doesn't become m cubed, for example. So once again, there's another 6 here, and m cubed, m squared. M cubed times m squared gives you m to the 5th right there. Now we got a negative, so I'm just going to put a minus there. 2 times negative 5 is negative 10. M cubed times m to the 1st gives us m to the 4th. And then 2 times 9 is 18. And then we pulled out all our m cubes, as we should have. Because once again, guys, we shouldn't have anything else remaining inside here that it's a greatest common factor among all 4 terms. If an m still remained, there's a problem. We didn't factor everything completely. All right, 4 more on this page here. And we still have another page to do a lot of other stuff. All right, number 11. Oh, with a lot smaller greatest common factors, by the way, guys. This is harder to be harder, just so you know. All right, 40uv cubed plus 100u squared plus 70uv. Now, this is degree 4. This is degree 2. This is degree 2. Are we in standard form? Degree 4. This is a tie. U is alphabetically before v, and this u is squared. So, yeah, we're in standard form there. I like it. All right, what number can we divide out of 40, 100, and 7? At most, I think it's just 10, right? So I can factor a 10 out of those 3 terms there. Now, u. Does u exist? Does u exist in all 3 terms? U to the 1st, u squared, and u to the 1st? Yes. Now, the smallest power of u is the one I have to pull out. So u to the first power exists here and here. So I'm going to factor a u out, just a single u. And then v. I have a v cubed here. And even though I have a v here, I don't have any v's here. So v is not a common factor among all three terms. I can only pull out a single u, and everything else that remains is going to have to stay inside. 10 times 4 is 40. U is right there, and v cubed is still inside there. So 10u times 4v cubed is indeed 40u v cubed. 10 times 10 is 100, and u squared, I still need an extra u there. 10u times 10u is 100u squared. And then 10 times 7 is 70. There's my u, and there's still a v that needs to be written there. So plus 7v. Let me fix that cube part right there. But that is my final result as far as factoring. Again, is the opposite of distribution. Number 12. Degree 7, degree 3, but of lesser degree because that u squared, and degree 2. Okay, we're in standard form here. So number 12. Check this out. I have even numbers in this odd number here, and the 2 is this one. I can't factor out a number this time. I cannot factor out a number. I'm only going to have to stick with variables in this case. Now, what variables can I pull out? All of them have a u. This one only has a single u, so the most I can factor out is a single u. And all of them have at least a single v with a v squared there, but the most I can pull out is v. So guys, I'm going to pull out u and v, a single multiple of u, or single power of u and v in both of these. And what remains? I still have the 2. All the coefficients will still stay inside, guys. I couldn't factor any numbers out of here, so that 2 is still here. U times what is u to the 6th? That's u to the 5th, and that v got pulled out, so it's there. So that's good. I got the minus 9. U times u is u squared, and there's my v. I already took care of it, so that's there. uv times negative 9u is negative 9u squared v. I got my minus 2. There's that u there. And v, I still need another v here to make v squared. V times v there. And then plus 6. And it looks like I took care of the uv, right? uv times 6 is 6uv. So that one pulls out right there. And that is the final answer. Once again, just recall, nothing here as a common factor that exists anymore that you can pull out. That's the end goal. All right, this one looks fun, right? I want to make sure we're in standard form here, so I'm going to rewrite this alphabetically. I got negative 8, and then yz to the 7th plus 24xz to the 6th. Now, this is of degree 8, and this is of degree 7, so it looks like we are in standard form. And if we're in standard form, guys, we are dealing with a negative leading coefficient, this negative 8 right here. Even if I couldn't factor out a number, which I totally can, like even if I couldn't factor anything out more than 1, I still want to factor out the negative. So a negative is definitely coming out of here. And then 8 and 24, I can factor an 8 out. Now this has a y, this does not. This has an x, this does not. These both have z's. I got to take the lesser amounts. I'm going to take z to the 6th completely out of there, and that's all that can pull out of here. Negative 8z to the 6th times what is negative 8yz to the 7th? Well, negative 8's already taken care of, so times 1. Remember, if nothing else could pull out, you just put a 1. But I'm leaving the 1 out because I can put other things in, such as the y and an extra z, right? Z to the 6th times z is z to the 7th. There it is. Now, a negative 8 factored out of here, right? Negative 8 times what is positive 24? Well, that's going to be a negative 3 when I factored out that negative. And then that x is still here. I never got to factor that out. And then z to the 6th, I factored that entire thing out, so that's what remains. So we get this right here as your final result. Very confusing looking. I don't know how it's helpful for anybody, but there it is. All right, and then number 14 here looks like in good standard form. That's degree 7, degree 6, and degree 4, and all alphabetical. Okay. We can factor a 10 out again like we kind of did that one time. A 10. A's, you betcha. A cubed, a to the 5th, a cubed. I can definitely pull out an a cubed. B's, no, because this doesn't have any B's. And C's, no, because that doesn't have any C's. So we can factor as much out as 10a cubed. 10 times 4 is 40. All the a cubes get pulled out of here, but the b squared, c squared still stayed within. We never factored those out, so there they are. 10 times now negative 3 here. 10 times negative 3 is negative 30. A cubed times a squared is a to the 5th. and then we're left with still a c right there because that never factored out. And then minus, so 10 times negative 2, and then the a cube's all pulled out, but there's still a b right there, and that's what remains. We are factored. So again, factoring is anti-distribution, guys. I spent a good long ordeal, 25 minutes there dealing with those ones on this front page, all right? Now, these bigger ones are not a huge expectation of some of the stuff we're going to do next, but let's start looking at the back. Now, the second page here, and it's the final page, what we have, we're going to start dealing with something called the zero product property. And this is going to introduce us to when we start hitting problems like 21 through 26, where we have to factor before solving using zero product property. All right, this is solve each equation by using the zero product property. That means we are actually going to solve for n and for x and whatever. We need to, right, this is an equation. I need to find out what value of n will make the statement true. These are factored. You can tell that there are parentheses around the stuff if we foiled, blah, 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 blah. But listen, guys, we're not going to foil. Being in factored form is of great benefit to us to solving this thing the way that we want to. Because when we're factored, we create what's called a product, a multiplication of something times something else. Now, there's this thing called the zero product property. And the zero product property is stated as such because it refers to taking a product of any set of numbers, such as two numbers like these, a and b, and the result being 0, the zero product property. A times b equals 0. Now, if you have a product that equals 0, if a times b equals 0, you know what has to be true? Either a has to equal 0 or b has to equal 0. Now, a and b could represent single numbers or quantities or variables, whatever they are. The point is, if the product equals 0, one of the numbers has to be 0. It is impossible. It is impossible to multiply two non-zero numbers and get 0. It's impossible to do that. Furthermore, as long as one of the numbers is 0, then your whole result is 0. So that's good. So what we're going to do, we've done conditional things before. We've created conditions with absolute values. We said either this or that. That's what we're going to be doing here as well. If we have a product of these two factors, this times this, treat this kind of like your a and b. If a times b equals 0, what we're saying is either this a, n plus 6 equals 0, or the n minus 2 equals 0. That's the only possible way that you can multiply these two things to get 0. So either n plus 6 equals 0, or n minus 2 equals 0. That's the only possibility of making this thing. Now the question is, now here's why we did all this. Because now we've created very simple solvable equations. I'm asking what value of n makes this single statement true. Subtract 6 from both sides, you get n equals negative 6. That's going to be one of your values. Or add 2 to both sides and you get n equals 2. So you go from some, and I'm not going to call this one complex, but you go from something that's all together in this kind of bigger way. If it was distributed, it would be more complex. But in this bigger way, and we break it down into conditions because of this special number of 0. This thing doesn't work for numbers that aren't 0. This is only special for 0 in this way. That as long as one number is 0, the whole result is 0. And that if you multiply two non-zero numbers, you're not going to get 0. Okay. So anyway, so that's the answer for that. There's more than one answer. There are two answers there. Two different answers. If I plug in negative 6 into here, I'm going to get negative 6 plus 6 is 0. And 0 times who cares equals 0. Or 2. 2 plus 6 is 8. 2 minus 2 is 0. 0 times 8 is 0. Right? So that's what you get. All right, number 16. Same thing, guys. We have a product. So let's create our conditions here. If x minus 5 times x plus 2 equals 0, either x minus 5 equals 0, or x plus 2 equals 0. One or the other is going to equal 0 in this case. Now, what would x have to be for the left quantity be 0? 5. Or subtract 2 from both sides, x is negative 2. And you're catching on. It's kind of coming into fruition pretty fast when these are factored like this and set equal to 0. All right, number 17. P times the quantity p minus 5 equals 0. Now, it might look weird for this not to be around parentheses, so put it around parentheses. The end result, guys, is it's still a product. This is like your a times your b. So just, don't let it confuse you, the fact that it just says p there. It's still multiplying by something. If p times p minus 5 equals 0, either p equals 0 or p minus 5 equals 0. If p equals 0, well then p equals 0. There you go. That's one of your values that you can use for it. But add 5 to both sides, you'll also get p equals 5 like that. And that's also another possibility. So it's one or the other. So again, don't be confused by it not having parentheses. The fact is it's still a part of the product. This should be more confusing, the fact that it's a quantity. Don't make it more confusing when it's not. All right, p plus 5 quantity squared equals 0. Well, this one's kind of interesting because it says the squared part. What do I distribute the square? Well, you never do that. What you could do, if you want to, you could write it as p plus 5 times p plus 5 just to kind of give yourself that idea of what you're multiplying. And you can still set up the condition, either p plus 5 equals 0 or p plus 5 equals 0. But you hear what I'm saying right now? That sounds a little weird. I'm saying the same thing twice. Either p equals negative 5 or p equals negative 5. Why are we saying this? What are we doing? Just say it once. If we square something to get 0, that something has to be 0. You don't need this two condition stuff. We can just sit it down to just 1. If p plus 5 squared is 0, then p plus 5 is 0. Because you know why? 0 squared is 0. So you don't have to do all that extra stuff. It's kind of weird to say the same thing twice in that instance. There's only one answer, and that's p equals negative 5. Now, you might have gone through all of these right here, guys, and you might have recognized a little something that was maybe decent pattern. Mr. Robinson, your answers are just opposite of the number that I see in here. I see a plus 6, you got minus 6. I see a negative 2, I see a positive 2. Minus 5 plus 5. You can see that pattern there possibly. Mr. Robinson, does that always happen? It always happens when you have a linear factor with a coefficient of 1, of a positive 1. So I could tell you right now on number 19, as this is a zero product property in factored form, k minus 5, I could tell you guys right now that this is k equals 5. If you want to save yourself a little step-a-roo there, you can do that. But don't tell yourself right now that this is also k equals 5 here. This one's a little different. Now there's a 3 in front. That's going to change things here. Let's take a look at what's going to happen when you set up your condition. If 3k minus 5 equals 0, there are 2 steps to still solve for k. It's not just adding 5 to both sides, but we do. 3k equals 5, and then we divide both sides by 3. See, this one's different. You get k equals 5 thirds. There's something, you can still do this mentally a little bit if you know how to get to that, and I advise you not to. But you can tell that, when you have a positive 1 in your linear factor right here, then yeah, it's just going to be the opposite of it, because you're just, just add it to both sides. Because 5 minus 5 is 0. But 3 times 5 minus 5 isn't 0. No, 3 times 5 thirds. Right? So you still got to work that one out. That's an instance of that. Let's see another bigger instance of it for both of these right here. Let's try and solve these ones. If 8n minus 5 times 3n plus n equals 0, either 8n minus 5 equals 0, or, and I know I didn't put the or here, my bad, or 3n plus 7 equals 0 here. I'm going to add 5 to both sides, and then I'm going to divide both sides by 8. So, you're going to see fractions come into play in these instances like this. It's the nature of the beast. Subtract 7 from both sides here. 3n is negative 7. Divide both sides by 3 gets 8n is negative 7 thirds. So there's my this or that case. And yeah, you're going to get fraction answers for some of them. That does happen, and it's something you just got to kind of be aware of. All right, guys, last 6 problems here, 21 through 26. Now, this is what everything that we did before has led to. We did greatest common factor on the front side. We just used zero product property on the back. You can see the instructions have not changed. In fact, now it says find the greatest common factor when necessary. Now it's necessary. We have, these are not basic solving equations where we can just get n by itself as a, move things over to the other side like that. Because I have an n squared term and I have an n term. And they can't combine, and I can't get a single n term by itself on its own side of the equation. Naturally. Not like in a way that you just want to move some things over. We're going to have to do a little more. We got to get a little more creative. What we do have the benefit of is this thing is set equal to 0 right now. And you have an instance of thinking that, hey, right now I have what's called a difference. I have a subtraction of two numbers. And it's not true that if a minus b equals 0, then a equals 0, b equals 0. It's nothing like that. But for a product, it would be true. You said, hey, I have a difference right now. What if I could turn it into a product? What if I could find a common factor, a greatest common factor? It's going to be important to get the variables out. What if I could find a greatest common factor of both these terms here? And in doing so, I will then create myself an opportunity of using the zero product property. Ignoring the equals 0 right now, just looking at this expression right here, if I asked you what is the greatest common factor of here, everything we did on the first page, you would mention that the 3 can be factored out, and with an n squared and an n, I could also factor out a single n. And what remains when I factor this thing out? 3n times n is 3n squared, and 3n times, well, 3 times negative 6 is negative 18, and there's the n that goes right there. So there it is, 3n times n minus 6. And hey, there's my equals 0, by the way. That equals 0. You know what I just did? I just created a product. When I factored it, I created this times this. And I don't need parentheses for that part to state that. I'm just showing you that it's 3n times n minus 6. Not to distribute back, you just came from there. We can now use zero product property. This is a product set equal to 0. And if a times b equals 0, then either a equals 0 or b equals 0. So we just took something that was ultra complex in that it was quadratic by nature, and we've created it into the most simple equations that we can use to solve. Divide both sides by 3, 0 divided by 3 is 0, n equals 0. That's one of your answers here. Or add 6 to both sides, you would get n equals 6. And we've kind of talked about how we know it's just the opposite of that number there when we have it. So, or n equals 6. And, you know, that was the answer to the original equation. We had to find out values for n that would make this statement true. This is the only one I'm going to double check on, but take a look at this. Let's try and substitute 0 in here. When I get 3 times 0 squared minus 18 times 0, let's see if we get 0. Well, yes. That 0 squared is 0 times 3 is 0 minus 18 times 0 is 0. So 0 equals 0. That one seems to check out. But that's not your only answer. There is another answer, and it's 6. Let's try that one. 3 times 6 squared minus 18 times 6 equals 0. 6 squared is 36. We got to do exponents first, by the way. 6 squared is 36 times 3 is 108. Negative 18 times 6, 18, well, it is 108 there. So 108 minus 108 equals 0, and that's 0 equals 0, so that checks out. So those two answers equal 0. They're the only two answers that equal 0, and we were able to accomplish it by seeking a greatest common factor and using the zero product property. Remember, you cannot use the zero product property unless you are set equal to 0 and you have a product of your values. All right, number 22, and I'm not going to double check for the rest of them. 4b squared plus 4b equals 0. Let's go ahead and find a greatest common factor. Pretty straightforward. 4 can divide out of 4 and 4. And for b squared and b, I can pull out a single b from there. b times b is b squared, and that gives you 4b squared there. And 4b times 1 is 4b. Do not forget that 1 there. Just because you factored out doesn't mean it disappeared, right? What do you multiply to get there? All right, once again, we have another product here. 4b times b plus 1 equals 0. So either 4b equals 0 and therefore b equals 0 if you divide both sides by 4. Or if you know my fast mode on this right now, it's just the opposite of this. That's b equals negative 1. So this or that, kind of, not really double checking, but all right, number 23. I got 4 more problems to do, and then we are all done. Number 23 here. 5x squared minus 35x equals 0. Maybe you're getting pretty good at the common factor stuff here. I can factor out a 5x, 5 out of both 5 and 35, and an x, just because that's x squared and that's x. So 5x times x is 5x squared. 5x times negative 7 is negative 35x, and that's set equal to 0. I now have my product. If 5x equals 0, then x equals 0. Honestly, guys, the 5's not even a part of it. Honestly, guys, I could divide both sides by 5 right now, and that changes nothing. But the 5 isn't really a part of it. It's the x that's important. It really is. It's the x that's important. If 5x equals 0, then x equals 0. If x minus 7 equals 0, then x equals 7. So those are your two answers there. You might have noticed that 0 seems to be an answer among all the ones that we've had in this number 21, 22, and 23 stretch. And you wouldn't be wrong, guys. As long as there's a greatest common factor that involves your variable, 0 is going to be one of your answers. And I want you to think about why this is. Notice that this is set equal to 0. Each term has your variable in it. What if we could plug a number into here that wipes everything out? If I plug in 0, these go away and turn into 0. Yeah, 0 is going to be one of your answers. That's why that common factor is so crucial, not only to figure out one of your answers, but also to figure out this one, because you need this to be a linear factor instead of quadratic, the way this is. Okay, number 24. 6n squared plus 15n equals 0. So I can factor a 3 out of these two numbers here. A 3 and an n as per usual. But here I still have a 2n that remains, right? 3n times 2n is 6n squared. And then 3n times 5 is 15n there. So 3n times the quantity 2n plus 5 equals 0. If 3n equals 0, then of course n equals 0. There's kind of that fast pace here. But don't just put negative 5 because now you got a 2 right there, right? We've kind of brought that up before. So 2n plus 5 equals 0 is the other option. That's our other outlet. So, or 2n plus 5 equals 0. I subtract 5 from both sides. I get 2n equals negative 5. And I divide both sides by 2. I get n equals negative 5 halves. You might have noticed, guys, I'm not writing decimal answers. I know it's negative 2.5. Improper fractions are great. They're fine. Please just leave them at that, like that. That's totally good. So n equals 0 or negative 5 halves. And I'm not going to bother plugging in negative 5 halves in there. But you can trust that it does work. And that's why we don't guess and check these things. All right, number 25. Now, this one's a little bit different, as well as 26, because it's not set equal to 0. That doesn't mean we can't set it equal to 0, and we very well should, would, and could. You got to be careful also saying things about what you want to divide by. Don't divide both sides by n. Don't divide by possible solutions. We can factor variables out, but we can't divide them out. You could divide by 4, but for the sake of the argument, we'll factor out the 4. So let's set it equal to 0. Let's start by setting it equal to 0. I'm going to subtract 8n from both sides. I'm going to actually make this seemingly more harmful by moving more n's that can't combine on the same side of the equation like this. So 4n squared minus 8n, and that equals 0. Now I'm at where I was with my other problems. I can seek a common factor among these, and then I can use the zero product property to kind of just, crack it, solve the rest of it. So factor out, looks like a 4n can factor out of both of these terms here. 4n times n is 4n squared. 4n times negative 2 is negative 8n. And there's my factored form. Zero product property states that if 4n equals 0, then n equals 0. Or if n minus 2 equals 0, then n equals 2. We've seen a couple of those before, and we're kind of running out of time for what we should do that. I'm just moving on. And lastly, number 26, same idea as before, guys. Let's get all of our terms on one side of this thing here. Let's subtract the 6r from both sides, and of course, make sure you combine it where you're supposed to. So I'm going to combine it right there. So I'm now going to get 4r squared minus 22r, and that equals 0. Okay. Now I can find a greatest common factor among these two here. I can't divide a 4 out, but I can divide a 2 out. So 2 and, of course, an r there. And I'm left with inside, I got 2r. Looks like 2r times negative 11 gives me negative 22r. So 2r times 2r is 4r squared. 2r times negative 11 is negative 22r. That equals 0. There's my zero product property in play right here. If 2r equals 0, then r equals 0. That 0 answer seems to never be leaving us. No, it won't. Not until we do other kinds of factoring. And then, or if 2r minus 11 equals 0, let's add 11 to both sides. And then divide both sides by 2. We get 11 halves like that. So this or that, and that's our final answer. All right, guys, those last 6 problems were really the goal of everything that we did there. We had a greatest common factor thing to play with to get to this idea at this stage of what we were doing. And zero product property, of course, to get this stage and get this idea of what we're doing here, all to lead into these solving equations this way. These quadratic ones with a linear term that you couldn't combine and solve a different way. So that ought to do it for this one, guys. This is Mr. Robinson. I thank you so much for watching this thing, and I will see you in the next one. Take care.